So this lesson is on distance, speed and time, which is very similar to displacement, velocity and time, but slightly different. So hopefully we'll get into that by the end of the lesson. So we're going to look at the difference between scalars and vectors. We've never heard them before. Calculate speed and velocity. And we're going to interpret distance, displacement, time graphs. So just to get you started, hopefully this should be a little bit revision for you. We're going to just write in the formula for speed. And speed is distance, hopefully you would know this already, divided by time. Distance, SI unit is meters, time is seconds. So that means speed is meters per second. I'm going to put this into the box here. So speed is distance divided by time. So have a go at this, pause the video, and then I'll go and show you the answer. Okay, Seb walks 200 meters in 40 seconds. What is his speed? Well, speed equals distance divided by time. Please always put that in. Distance is 200 divided by 40 seconds. 200 divided by 4 is 20 divided by 4, which is 5 meters per second, even without a calculator. So very straightforward. I would imagine most of you should have been able to do that without too much of a problem. Here's a few more. See if you can have a go at doing these. Pause the video here, and then I'll go back and go through them. Lucy covers 2 kilometers in 100,000 seconds. What is her speed? Speed equals distance divided by time. Distance in this case was 2 kilometers, so I'm going to have to change that to 2,000 divided by 1,000 seconds, which is 2 meters per second. How long would it take Freddie to run 100 meters if he runs at 10 meters per second? Well, speed equals distance divided by time. If we need to draw the triangle, speed equals distance divided by time. Time equals distance divided by speed. Time equals distance divided by speed. The distance was 100 divided by 10, which comes out as 10 seconds. Sue travels at 50 meters per second, that's the speed, for 20 seconds. How far does she go? Distance equals speed times time. Speed is 50 meters per second times 20, which is 1,000 meters. If you want to, 1 kilometer. Hannah drives her car at 85 miles per hour. That's about 40 meters per second. How long does it take her to drive 20 kilometers? So we've got to be careful here with our units. They've given us 80 miles per hour, but they've also given us 40, so we're going to have to work with that one because that's the one that's going to work together. How long? Speed equals distance divided by time. Time equals distance divided by speed. The distance was 20 kilometers, 20,000 meters in 40 meters per second, which is 2 zeros on the 20 divided by 4, which is 500 seconds. Hopefully all reasonably straightforward. Let's turn on to this next page, this nice slide. Okay, well, we're using the word distance, and I'm sure most of you understand what the word distance is. Distance is really just a measurement of how far you travel. So in this car, you can see Citroen 2CV, car has travelled 200 meters. Well, a word I'd like you to introduce here, it's almost the same as distance. But displacement is a word that we use for distance when we also specify the direction. It's an example of what we call a vector. Distance is an example of what we call a scalar. It just has magnitude. Distance is a vector. It has the same magnitude here of 200 meters, but we also specify a direction. Think where we specify direction in physics, we would call that a vector. We have exactly the same thing here for speed and velocity. Speed is a scalar because it just has a magnitude. In this case, this 2CV is traveling at 20 meters per second. If I give you more information here, and I say it's 20 meters per second east, well, that would actually be the definition of what is the velocity. So maybe if you've heard the word velocity before, which I'm sure you have, they are very similar idea to speed. It's both measured in meters per second, but if you actually want to give the overall velocity of something, you also need to include a direction. So the formula we've been using so far was distance equals speed divided by time. So I can use speed equals distance divided by time. So that gives us three formulas here. Distance equals speed times time. Speed equals distance divided by time. And time equals distance divided by speed. The same formula, but written with vector equivalents. Well, time remains the same. Speed now becomes velocity, which is v. And displacement, confusingly, this distance now becomes displacement. And confusingly, the symbol for displacement is s. It's related to the word space. So another way to write, so these are sort of analogous formulas. These are just the vector forms. So this is really saying displacement equals velocity times time. And then we can say velocity equals displacement over time. And we also have time is displacement over... Now, so it is a bit confusing because this S here is displacement. And this S over here is speed. Hopefully you'll get used to it, don't worry. Okay, let's carry on. So let's make some list of some common scalars and vectors. Well, two obvious ones we can go with is distance, and that's matched up with displacement. We also know we have speed, and that's matched up with velocity. Here's some scalars. Time is a scalar. Time, you just measure time. It doesn't really have a direction as such. Another common scalar is mass. Mass is the amount of stuff that you're made up of, which is really a measure of how many atoms you're made up of. So that is a scalar. What about some vectors? Well, a common vector that we will be coming across soon is one called acceleration. All forces are vectors, so that makes weight as a vector. Now, weight I wouldn't exactly say they pair up in the same way that speed and velocity and distance and displacement pair, but they are very closely connected. Mass is how much stuff you are made up of. Weight is the effect that gravity has on the mass. And weight clearly has a direction. Weight is always a direction towards the center of the mass of the object. Let's see, give you one more example. All forces are vectors because they all have a direction. So we could also go with friction. And upthrust, there'd be another one. And drag. Anything that's a vector is, anything that's the force is a vector. So just all forces in general. And they are probably all the ones that you need to know. So, what are we looking at here? We are looking at a displacement or a distance time graph. And what you need to be able to do is really just understand what these lines mean on a displacement time graph. So give yourself a bit of thinking time, have a look at that graph and see if you can work out what you think is going on with this object in the different stages, and then I'll come in and help you fill in these words. So if you look at the start here, we've got an object and its distance is getting further away from us over time. So in 20 seconds, it goes from being right next to us, 0 displacement, up to being 10 meters away. And it's doing that at a steady rate. This is what I would call constant velocity. It's got a constant velocity. I can tell that because the line is straight. What's happening in section 2 here, horizontal line on displacement or a distance time graph? Well, it starts off at 10 meters and 20 seconds later it's still 20 meters away from us. This object is not moving. This object, the best physics word I can use for it is stationary with an A. That's an A, not an E. If it was an A, we'd be talking about paper. Now, what about 3? Well, it's very similar to what was going on here. This travelled 0 to 10 meters in 20 seconds. This has travelled from 10 meters away to 40 meters away in the same time period. This is also a constant velocity. What's the difference? Well, it's going faster. 4. We've got a nice diagonal line. So it must be constant velocity, but look, the gradient is now negative. This has got a negative gradient. Sloping back, negative gradient. This is a constant velocity, but probably more importantly, it's changed direction. Very good. Okay, have a go at those questions and then I'll come back. What is the velocity during the first 20 seconds? Well, let's go back here. We'll work, let's go back. SVT, SVT. What's the velocity? Well, the velocity is the displacement divided by the time. What was the displacement in these first 20 seconds. Look, in the first 20 seconds it moved 10 meters in a time of 20 seconds. 0.5 meters per second. How far is the object from the start after 60 seconds? Well, I'll just do it on this small one here. If you need to turn back. 60 seconds, look. 60 seconds, straight up here. Straight across here. Reading off the graph, it was 40 meters. What's the velocity during the last 40 seconds? So this is here, 60 to 100. That's the last 40 seconds. What is the velocity during the last 40 seconds? Well, velocity is displacement divided by time. It moves, comes back 40 meters. So I'm going to go for, I'm actually going to write minus 40 there. I suppose I could really get away with that because it's coming back. It is a vector. 40 divided by 40, and its velocity here is minus 1 meters per second. The minus sign here is because velocity is actually a vector, and we're actually indicating here that it's traveling back. It's traveling in the opposite direction to when it was traveling at 0.1 meters per second. When was the object traveling the fastest? Well, I can actually calculate this, but I can see it quite clearly. It's where this gradient was the biggest. So I can really see it's from 40 to 60 seconds. If I wanted to prove that, let's do it very quickly. Velocity equals displacement divided by time. What was the displacement? It went from, travelled from 10 to 40 meters. That's 30 in, how long? 20 seconds, which is 1.5 meters per second. Little extension task for you. Swimmer starts here. He swims 3 lengths in 150 seconds. What distance has he travelled? What is his displacement from his initial position? What is his average speed? Okay, so he starts here, but he goes down, comes back, goes there. So he's doing this. Boom, boom, boom. What distance has he travelled? Well, he's gone 50 meters, then 50 meters back, then 50 meters. So he's travelled 150 meters. What's his displacement? So really that means how far is he from where he started? How far is he from where he started? Well, he's actually only 50 meters. He's actually 50 meters. We go with this compass sign here. He's 50 meters east of where he started. Both measured in distance, both measured in meters, one a distance and the second one a displacement. What was his average speed? Well, speed equals distance divided by time. 150 divided by 150 seconds, which is 1 meter per second. What was his average velocity? Well, velocity is, this S is now displacement divided by time, but he's only 50, he's only moved 50 meters because he came back, so he's actually only 50 meters away from where he started, so his average velocity is 150, which is 0.33 2 sig figs meters per second. One thing missing here, this is velocity, it's a vector, and it is 0.33 meters per second east.